Hi, I'm Karen, the social media ninja and assistant on The Ben Heck Show. Sometimes we have extra footage that we can't quite fit into an episode, or we just want to share more details of the projects with you. Look for bonus content videos like this one on the Element 14 community, found on element14.com/TBHS, and click on the, you guessed it, bonus content section. And don't forget to look for me online as The Heck with Karen to give me your questions and comments about the show.
We're doing a future episode where we're going to make a consoleized Game Boy, specifically a large Game Boy, a Game Man. So we're going to use the FPGA for that. And that's something that FPGA will be really good for, taking high-speed signals intended for the LCD screen on the Game Boy and turn them into VGA signals. So I'm going to do a little research first. See, the Game Boy is 160 by 144 pixels, okay? Although they're showing a Game Boy Color here, which isn't the original Game Boy, but that resolution sounds right. So 160 by 144, wow, that's pretty crappy. Okay, so it's 23,040 pixels. Now, if we had 1 byte per pixel, which we don't really need, that would be 23K, which we might have enough for on the FPGA, but I don't know. A better way to do it might be to just pack the bytes. So if it's 160 pixels across, but it's only 2 bits per pixel, that means if we could get 4 pixels in a byte, because a byte has 8 bits, and we'd have 4 pairs of 2. So we could take 160 divided by 4, means we'd only need 40 bytes per line to store the data. Multiply that by 144, and we get 5.7K. That's a lot better. Now, we'll probably want to have a double buffer, so we'll read in 1 frame from the Game Boy while we're sending another frame to the VGA screen. So whatever RAM we think we need, we'll actually need twice that. So take that times 2, 11K. The Game Boy would have used character-based tiles, which would take even less RAM than that, but this is the future. We have plenty of RAM. The Game Boy is one half the equation. The other half is the VGA display. So I just did a Google search here for some images. This one's not perfect, but it looks pretty good. So it's actually clocking out more pixels than you actually see on the screen. All displays have something called a vertical and horizontal front and back porch. And that is a certain amount of spacing before it starts drawing a line. After it draws a line, then there's an H-sync, starts over, does it again. And then there's also blanks at the top and the bottom. So we have to find out what the front and back porch signals are for our particular display before we can have a chance of successfully driving it. This is a good site, I've been to before, tinyvga.com. If you scroll down, let's see. All right, so this one looks pretty good. 1280 by 1024 at 60 hertz, which is the same rate as the Game Boy screen is updated. Pixel clock, 108 megahertz. Okay, that's a nice even number. So this is going to tell us what we need to put in for our front and back porches. So front porch is 48 pixels, sync pulse is 112 pixels, back porch is 248. Okay, so the information we need is right here. I should bookmark this page. I think we'll start by actually trying to get the VGA signal up and running. We'll get some colors on the screen. Then if we can do that, we know we're at least talking to it. And then we'll attach the Game Boy. Let's create a new project. Okay, we need the F17C6. Okay. All right, so now we need to create some files. Let's see, new. I'm going to do a Verilog. So this will be our main file. Now in true programming fashion, I'm just going to copy some stuff from another file that I have. Start with the module. Now this name has to match the name of our file, which we haven't given a name yet. I was never given a name. Let's see, LCD VGA. Save this, give it the same name. Oh, okay, well, we missed end module, otherwise that should be good. Okay, nothing's hooked up, but it looks like it's not complaining about it. So we just grabbed these from another file, but let's put them to where we actually, let's make them correct. Let's take a look at VGA. Okay, red, green, blue, ground, H-sync, V-sync. There are also I2C lines on here, so that's how your computer detects what the monitor is. We don't need those. So you'd think we just need 5, but since we're actually going to create a resistor ladder, so we have 4 shades of gray for each color, like the Game Boy, we actually need 2 bits for each one of the colors. And we're going to put that through a resistor ladder, which will turn the digital signal into an analog one. Okay, so let's type in what we need. Clock 50, that's going to be the crystal coming in. Let's call it red 0, red 1, green 0, green 1, blue 0, blue 1. Okay, so we'll be sending 6 lines out and then putting each one through resistors, combining it into 3 lines for the colors. Okay, we also need H-sync and V-sync. The capitalization of this is important, so we have to make sure that if it's lowercase h, uppercase s, you keep everything else that way. Down here, we're going to define what they are. The clock is an input, but now, since we're not in this list, we need to put a semicolon at the end of it. Okay, the rest are going to be outputs. We just type them in again. Red, green, blue. Got to remember that. In today's thrilling episode, Ben types things into a computer. Okay, let's see if this compiles. Save, yes. Okay, now we're going to go into the pin planner. We've created these connections, and now we have to say, okay, where do they actually connect on the FPGA? And that's what the pin planner is for. Let's load this up. And of note, you have to do a compile here before the pin planner will actually show you the values you want. But now we can see they're in the list, but they're not connected to anything. So now we have to connect them to things. I have the PDF of the dev board here. Well, we don't need a whole lot, so let's use GPIO1, which will be that bank. For some reason, they've listed it here as GPIO, but then that connects to the pin underscore A4, A5 numbers that you have here, you know, A6, so A down, 6 over. So we're actually going to have to figure out what the numbers all are. Let's just start with 1, and then I'll do the rest. Let's see, GPIO18 equals pin E7. Okay, let's go back over here. So let's just do red, green, blue, just so it makes sense in our head. Output, okay, let's see, location, red 0. Double click this, you should be able to just type it in, pin E7. So let's change that to 3.3 volts. Okay, the next one was 19. D8. So if we want to have this pin, this is red 0, red 1. I wish they would have just labeled this by its FPGA name. So again, we go back over here. So for the next one, pin underscore D8. Okay, make sure both of these are the same voltage. And as we create these, you'll see them start to fill in on the map. So I'm going to fill in the rest of these. I filled in all the pin assignments. 2 bits of blue, 2 bits of green. I hooked up the LED indicators just so we have a heartbeat, 2 bits of red, V-sync, H-sync, and the clock. And they're all outputs except for the clock, which is an input. I combined some of these back in the Verilog. We have output 7 down to 0 LED, 2 bits each for the red, green, and blue, and then these are just singles. Okay, let's just make sure this still compiles. All right, we're still doing okay. I'm going to hook up the VGA. I mean, we've got a ways yet before it's actually going to do anything. Felix created this resistor ladder for me. H-sync, V-sync. I find it helps to wire things in the order that you might say them, like red, green, blue, RGB. Wire them in that order. Why make it harder for yourself? Now we're going to create a phase lock loop function to change our 50 megahertz clock into a 108 megahertz clock. We're going to go to Tools, Mega Wizard, Plugin, Manager, create a new mega function. Yes. Okay, we want Verilog, Alt, PPL, phase lock loop. Pixel clock, there we go. So it's going to ask us a bunch of questions, and then it will create a function that will give us our desired result, which is a 108 megahertz clock signal. Okay, 50 megahertz is the input of the clock. That's the crystal that we have on the board. Okay, next. We don't need that, we don't need that. So it's in clock, out clock. Okay, automatic. We don't need a second clock. Okay, this part's important. Enter output clock frequency. We're going to request 108 megahertz. So it's actually multiplying by 54, then dividing by 25, our original clock, to get 108. So it can get us that pretty much on the nose. That's good. All right, let's hit next. Okay, we could create additional clocks if we wanted. We don't need to, but we could always come back and do that. And you can come back and change this at any time. So if you take this same design and swap it to an FPGA with a different clock built into it, you could just go in there and say, okay, our input clock is now 25 megahertz. Okay, now we've created our pixel clock. Okay, now it created its own Verilog file. Let's take a look at that. Okay, so this is the important part. The module pixel clock, in clock, and then C0 is the out clock. we need to connect this to our main V file so it will use this code. But this is the code that actually creates our custom clock. Okay, so we're going to put this in our main Verilog, and it's going to be pixel clock. Okay, and then here's the things we're passing into it. Now, if you remember over in the pixel clock, we have in clock 0, C0 right there. So those are what's used to connect it. Go back over here. We're going to change in clock to clock 50. So we're going to pipe in the crystal into this other function, and then we're going to get back. Let's call this, I don't want to call it pixel clock again. I'll call it dot clock. Well, we might use that somewhere else. How about VGA clock? There we go. All right. Okay. That should connect them. Let's see if it still compiles. Hopefully I didn't ruin anything yet. Seems okay. Okay, let's test to see if that clock's actually working. I've added some code here to test our clock. We have an 8-bit LED register and a 16-bit counter. So always at the positive edge of the incoming VGA clock, this is what you'll do. Increment the counter by 1, and then put the 8 LEDs to be the 8 upper bits on the counter. All right, let's see what happens when we flash this. The LEDs are all lit, so they are changing. They're just changing so fast we can't see them, nor can the camera. Okay, I switched it, so we're now looking at the top of a 32-bit counter. So even though it's going really fast, it takes it a lot longer to count up to 4.2 billion. So now the lights actually look like something. So even though it's still counting at the same rate of 108 megahertz, it's counting up to a larger number, a 32-bit number, which takes quite a while. It's like 4.2 billion. So now we can actually see the lights changing. So we mapped the LEDs to the top end of a 32-bit counter. Unlike a microcontroller or a CPU, FPGAs do everything in parallel. So we could just leave this code here for the rest of our demonstration, and it will always blink those LEDs. It won't affect the rest of the program because remember, FPGAs, you're actually building real circuits, and you can build one over here, one over here, one over here, and they all work in parallel, which is pretty cool. That's a big advantage of an FPGA. We definitely want something always at the VGA clock, but I think what we want to do is actually try to drive some pixels now. So we need to look at our sheet. Okay, so the horizontal timing, there is 1,688 horizontal pixels, only 1,280 of which are visible. And the vertical timing, 1,066 total lines, 1,024 are visible. So we need to start putting in some parameters. So you can use registers, but if you use a parameter declaration, it kind of, well, it's what you would call a constant in other languages. Parameter, if I can spell it right. And then just to be cheap, I mean, you can set, so this is how many bits, 15 down to 0 or 16 bits. You can try to get it exactly to the number. I mean, you don't need 16 bits to create the number 1066. But usually in programming, we're used to thinking of bytes, words, longs, or shorts, or int 16s. So this would be like a short word, int 16, 16 bits, or 0 to 65535 positions. Yes. Okay, so I'm going to make one called H counter. That's going to be the horizontal pixel counter. And then I'm going to make another one called V counter. Oh wait, actually no, if those are the counters, those would be registers. So, my forgotten. What we want to use the parameters for are the porch settings. Okay, again, this is kind of overkill to use a 16-bit number for this, but it's easy to remember. Okay, so the horizontal front porch is 48 pixels. So even though it's not drawing pixels, it's still being clocked at the pixel rate, so we just consider it to be pixels. Back porch is 248, 15 down to 0, let's key. VBack is 38. Oh, I forgot an E there. Parameter 15 down to 0. The front, just 1. There's also something else we need to consider, which is the sync. Sync is normally high, but when it goes low, that tells the system to, change lines. Of course, we already have something called H sync, so we should probably call this I'm gonna call it H-sync pulse. H-sync pulse is 112. That means it pulses for 112 pixels. So basically what happens is you have the back porch, which is just nothing. Then you have the active pixels. Then you go to the front porch. And then at the end of the front porch is when you have your H-sync pulse. And that's what tells it to start all over again. So you actually have to have a certain amount of back porch, certain amount of pixels, certain amount of front porch, and then a certain amount of H-sync after the front porch in order to make a line repeat. And they still do that now with modern LVDS or HDMI monitor signals, so it's still relevant. 15 down to 0, we'll call that the V-sync pulse, equals 3 lines. Okay. So I'm going to change these. H back will still be the same. H front will be, let's just comment out the correct value just so we have it. Oh, yeah, sorry, I forgot what language I was in. So H front is going to be 248 plus 1280, so that's where it starts. And then H sync pulse is 248 plus 1280 plus 48, which means we actually need one more. I'm going to call H total equals 248, so it's the back porch plus the visible pixels plus the front porch plus the sync pulse, and that's your total. I just typed it out to make it look a little bit more obvious, so we can obviously, put in the correct numbers, although this will compile. Okay, I'm going to do the same thing for the vertical. Okay, so I copied the always at positive edge VGA clock here. So let's just always be increasing the H counter. Now this is a little different from other languages. I have to assign H counter equals H counter plus 1. Okay, that's going to increment it. Okay, so that's always going to happen. Now when you do stuff with Verilog, you kind of have to do it as a state machine. Everything's either one way or another. If H counter is more than H back and H counter is less than H front, okay, we'll create another reg. We'll call it active pixels equals 0. So if that is, so basically if it's in the active draw area, active pixels we'll set to 1. Now here's the thing, you should always have every possible state accounted for. So if it's in the active area, set active pixels to 1. If it's not, set active pixels to 0. You always have to have one state or the other. I mean, you might be able to compile it without that, but it might not work. Okay, so what we can try here is I'm gonna actually just, I'll just get rid of that. All right, I'm gonna comment that out. And then we can attach LED, 0, attach that to active pixels so we can see the result of this logic. I've connected the active pixels to LED 0, and LED 0 looks like it's just solid on, but if we hook it up to the scope, so the high areas in the scope, that indicates the actual time when we'll be drawing pixels. So this represents 1,280 pixels. What I'm going to do next is actually attach the horizontal sync to this, and that will be more of a proper signal. And at that time, the scope should actually be able to say, oh, this is running at the frequency that the horizontal sync will be at. So the scope was showing the active area for the active pixels, but what we really want is the sync pulse. So let's do this. If H counter is more than, actually let's make it more than or equal to, more than or equal to H sync pulse. Okay, so if that's the case, then what we're actually going to do is we're actually going to affect the actual H sync. So our actual H sync wire here. Okay, so H sync is normally high and it only goes low for the pulse. So if it's more than the pulse, we actually set it to low. Else, most of the time, it's going to be high. Okay, H counter. If H counter is more than H sync pulse, H sync less than, I'm sorry, H sync is connected to that. All right, let's test that out. All right, we have some good pulses on the oscilloscope, so now I'm going to try to add color. Right now the screen is just blank. So it's getting the sync signals through VGA, but there's nothing to display. So right here I created this. If H counter is more than H blank and V counter is more than V blank, basically that means if it's an active pixel on the screen, I made a variable called active pixels. So we can use that down here as well. So first there's an argument that sees if, there can be active pixels. Then we go, if active pixels, then we'll run all this stuff. If active pixels, which means, okay, we can draw pixels. Unlike a HDMI or DVI or LVDS, you can't actually be drawing pixels while you're doing the sync. You have to turn off the video. You have to make it black. Let's just try something here. Red, 1 down to 0. And make that 3. And again, everything with FPGAs has to be in a certain state. So it's like, okay, so if it's active pixel area, make things red. Else, again, there always has to be the other state of it, the binary of it. Else it is black. Okay, let's just try to make the screen one color. We take one step at a time. Sure, now it compiles. Okay, it's done. All right, so let's go to the programmer and let's see what happens. Yeah, red screen, sweet. Okay, that's a good start. We have something on the screen. We can do anything now. One thing to think about with Quartus too, I like to leave the programmer window open. I'll put it on another monitor here. If you keep hitting this button over and over, you'll open multiple copies of the programmer and they might not be up to date. So just, leave it open all the time. All right, I'm gonna do a few more things. We're still gonna leave this at, well, actually we'll do this. So if active pixels aren't on, then turn everything black. Like that. Blue, green, red, that's like backwards. Gross. Okay, but up here, we're gonna put more arguments in. Let's do this. Okay, if active pixels, okay. If H counter is less than, 800, begin, end, else. Remember, we're using begin and end just like you would curly brackets in another language. Let's do this. Red equals, red 0 down to 1. So the reason I have to do 0 down to 1 is because I've set up red to have 2 bits. Therefore, I have to define what the bits are. Now, I have to make sure everything else is accounted for. So let's do blue 0, green 1 down to 0 is 0. Because you have to think there always has to be a state for everything. So if active pixels, which means if we're actually on the display, 1280 by 1040 in this case, then this code will execute. If we're not in active pixels, then it just makes everything black. But if we are in active pixels, then we're like, okay, if H counter is less than 800, this is what you set the 3 things to. But if it's more than 800, then you have to set them to something else. You can't just let them float. So I couldn't just say, red is this and just forget the other ones. I mean, by default, they'd probably just all be black. So if it's less than 800 across, it'll be red, and then halfway across, we'll make it blue and turn the red to 0. So see, it's either this or this. And something else to think about, you can never drive something from more than one location, because remember, this all is happening at the same time. Either this is happening or this is happening, not both, because then you're trying to drive the same register from 2 locations simultaneously, which you can't do, and the compiler will definitely tell you, hey, you can't do this. So this should make a red and blue screen. Let's see if it works. And once we know this is working, then we'll continue to subdivide it until we get virtual pixels that we can use for a Game Boy. Okay, compilation complete. Let's see what happens. Hey, there we go. I've created a few new registers. This is block X and block Y. And then we also have clock P. So we'll use clock P as the color, and block X will be a horizontal counter. Okay, so in active pixels, green equals clock P, okay? So if block X equals 7, basically if we count 7 across, then we'll change the color of clock P, so we'll actually see, it will subdivide it into fat pixels. If it does not equal 7, then increment it until it does. There is one other thing we have to think about though, and that's the vertical blocks. Well, let's just try this for starters. So these pixels are really hard to see, at least on camera, but this should make them a little easier to see. So we'll make them work horizontally and then we'll make them work vertically. It's not perfectly in sync yet, but as you see, I have a couple shades of green pixels. One of the counters is overflowing, which is why it looks like it's scrolling. If I reset the counter at both the horizontal and vertical start, it should stabilize it. But we're getting pretty close to simulating some big fat Game Boy pixels. Okay, so I'm changing the green value every 10 lines. Now I need to change it horizontally as well, and that should get us discrete pixels. Let's see. And once I have pixels, then I can attach it to RAM to create a Game Boy image. And I'm going to keep it puke green, even though, you know, it's a color monitor. All right, individual pixels.
If you liked this video, look for more videos on the Element 14 community by going to element14.com/TBHS and clicking on the bonus content section. You can also look for me as The Heck with Karen on Facebook, Twitter, YouTube, Google+, and the Element 14 community, where you can follow me to get even more behind-the-scenes content. I'll be seeing you online.